Okay, number 8. Why does buoyant force not depend on depth, assuming the object is fully submerged? So the reason it doesn't depend on depth is because the difference in pressure between the top and bottom of the object is the same everywhere. Now, I don't mean that the forces and the pressures are the same. I mean the difference between the pressures is the same. So if you've got objects under the water here, and you've got a couple different objects, here's one, and here's one further down, they're going to feel pressure acting on them. Okay? There's pressure from the sides, but that pressure is the same. So the side pressure doesn't really matter that much. Here's what does matter, the pressure from the top. And the pressure from the top and the pressure from the bottom are not the same. The pressure from the bottom is larger, so it pushes up. That's what causes buoyant force. The further down you go, the larger the up pressure gets, but equally larger the bottom pressure gets. So the difference between top and bottom is the same. So even though the values are not the same, the difference is. So that's why the buoyant force does not depend on depth. So the further down you go, it doesn't change your buoyant force. It doesn't change the buoyant force at all. Okay? All right, what property of an object most affects whether an object can sink or float? That is density. Now, it's not the material of what the object is made of, it's the object itself. So a solid cube has a very high density, but if you took that same cube and spread it out over a larger area with the same mass, you would lower the density. So it's the density of whatever the object has. Okay, discuss the 3 rules about sinking and floating. So if the object is less dense than the fluid, the object will float. If the object is as dense as the fluid, it will remain where it is. And if the object is more dense than the fluid, it'll sink. Okay, let's do an example with this sinking and floating thing. All right, if you need to move, you can come over here so you can see better. I'm going to do it over here at this table. I have a 2-liter bottle, and inside the 2-liter bottle, I have a stopper. And the stopper has some water in it, but it's also got some air in it. So for those of you close, you can kind of see there's a little air bubble at the top. Okay? All right, so density affects the object. What I'm going to do is I'm going to increase the pressure in this container. When I increase the pressure, it's going to force more water up into the stopper, and that's going to increase the density of the stopper. So as I slowly push this up and pump it, it's going to increase the density of the stopper, and at some point, there we go, I increase the density enough so that the thing sank. So you can look down now and you can't see the air bubble anymore. The air bubble is gone. And the reason it's gone is because I increased the density of the object by increasing the pressure. If I release the pressure, should have warned you, Mark. It goes back up and there's air bubble again. Okay? So again, the idea is increasing the pressure increases the density of the object. You gonna sink? Nope. You gonna sink now? Oh, right now, so right now I got the density perfect. So right now it's just staying where it is. It's not really floating, but it's not really sinking either. And one more function.
How many times can you squeeze that?
What? Like how much can you do it? You could do it forever.
I should try doing it like 30 times.
Should I? I don't want to scare Mark. You know I'm going to. But I wasn't then. And it goes back up to where it is. So pressure and density are the things that affect buoyancy. All right, you guys can sit back down. I'll have this up here. If you want to play with it at the end of the period, I'll leave it up and you can do that. That was my son's science fair project a couple of years ago.
I bet your son wins all the time.
No, I was a little confused on what the expectation was. So they wanted something a little bit different from what we were doing. Right? Or a potato battery. You haven't done those before? You can make batteries out of potatoes or out of lemons. Don't think so. All right. How is it that something really dense like iron can be made to float? You can increase its volume by, increase its volume without increasing mass. To lower density. So the key to your boat is to make the density small. And the way you do that is by taking the mass of your boat and spreading it out over a larger area, by making your boat large or wide or whatever, and deeper, so that it holds more air inside of it than it would if you just laid it flat on the water. Okay, principle of flotation. If buoyant force is greater than or equal to the force of gravity, the object floats. If it's equal, it technically isn't floating. It's just sitting at the same position without going up and down. But if it's already on the surface, that's essentially floating. And then lastly, how does the density of the fluid affect flotation? So it's easier to float in denser fluids. And again, the reason for that is the density affects the object sinking or floating. If you're less dense than the fluid, then you'll float. If you're more dense than the fluid, you'll sink. If you use a denser fluid, you'll be able to float easier because your density won't change, but the density of the other object will go up. And so it's easier to float in denser fluids. And again, the reason for that is because of how the densities balance out.
Is that why the Dead Sea is like super
Yes. Yeah. So the Dead Sea is very salty, which makes the water a lot more dense, and it actually makes the water more dense than people, and so you can float in it. Yep. Yeah, Salt Lake City is like that too, the Great Salt Lake. I don't think it's quite as extreme. I don't know if you can float super easy in it, but
If you just fill a swimming pool with a bunch of salt,
you can float in it.
wouldn't do that to our
You might need a lot of salt. Might have to go to the grocery store. Got to make a grocery trip. All right. Any questions on buoyancy and that kind of stuff? All right. Jump to the last page. All right. Let's do a couple of examples. Let's do the first example of an object that's floating. Okay. We'll do that real quick. And then And then we'll do an example for, we're going to solve, where are we time-wise? Yeah. Okay. So the supertanker Seawise Giant displaced 5.81 times 10 to the 5th cubic meters of water when it was fully loaded. What was the mass of the ship when it was carrying a shipment of oil? So this was the largest boat that's ever been created, and it was an oil tanker. So the first thing is we're going to draw free body diagrams, which are your force diagrams, for the object, and we're going to set up Newton's second law. Remember, the buoyant force on a floating object is equal to its weight. So we're going to draw the water. We're going to draw a big old giant boat. This is totally what the boat looks like. Yes, we are. We're going hunting for Jaws. Okay, there's my boat. And then we draw the forces. And there are only two forces for this problem. There's buoyant force up and gravity down. Okay, we're looking for the mass of the ship. And when we think about mass and displacement and density and all that kind of stuff, we think about this equation. Density equals mass over volume. Okay? So we know that the volumes, the amount of water, we know the amount of water that's displaced, and we know the density of the water. That's going to allow us to find the mass of the water. So use the volume of the fluid to find its density. So density, 1 times 10 to the 3, which is just 1,000 if you'd rather do that, equals mass. This is the mass of the water, 5.81 times 10 to the 5th, over the volume. Wait, oh no, I gave you volume, didn't I? My bad. I put this in the wrong spot. That's my bad. I know. Over mass. So, we multiply the volume to both sides. So 5.81 to the 5th times 1,000 to the 6th gives me a mass of 581,000. Sorry, 581 million. My bad. Ran out of zeros. Yeah, it's a lot. So, how much should the ship weigh? So if this is how much the water weighs, and the ship is floating, how much do you think the ship should weigh? 3 pounds? They're about, just give or take. If it's floating, it's going to be the same. Okay. All right. Let's take a short brain break. I'm going to tell you a story time.